4.4 concavity and then second derivative test. By the end of this section, you should be able to determine interval on which the function is concave upward or concave downward. Find any points of inflection of the graph of a function. Apply the second derivative test to find the relative extrema of a function. First of all, let's talk about the concavity. Let's say you have a differentiable function f. Now, when you try to plot the graph of differentiable function, the graph could look like this, or look like this. So sometime it goes up, sometime goes down, something like this. We can find out when it's it faces up or when it faces down. So here you can see that it's facing up, that's called concave up, and this part here the graph is facing down, that's called concave downward. And that can be found by finding the derivative of that function. Let's say function f, and if you find the derivative of that function, we can find out when this concavity happens. So let f be differentiable on an open interval I. The graph of f is concave upward on I, that interval, when this first derivative is increasing on that interval. And when first derivative is increasing, the graph would be concave up. When the first derivative is decreasing, the graph is concave downward. That's the definition. So let's try to understand the meaning of concavity one more time. Let's say you have a concave up graph like this, where the derivative of the function is increasing. The meaning of that is, at any point on this graph, if you try to draw a tangent line, as you can see that the graph would be always greater than that, above that tangent line. Okay, let f be differentiable on an open interval I. If the graph of f is concave upward on I, then the graph of f lies above all of its tangent lines on I. And if it's downward, the opposite happens. The graph would be below the tangent line if you draw the tangent line on that graph. That's called concave downward. To find the open interval on which the graph of function is concave upward or downward, we need to find the interval where the derivative is increasing or decreasing. How do you do that? Let's take one example, function f of x, which is 1/3 x cubed minus x. This is the graph of the function, the upper part here. And then this is the graph of the derivative of that function. As you can see here, I can find the derivative of this function by using the power rule, that is x squared minus 1. And if I plot the graph of this parabola x squared minus 1 here, how do we do that? That's a different story, but we can always find out the derivative, and we can find out where this derivative is positive, where it's negative, and based on that information we can say, hey, where is the first derivative is decreasing or increasing. If you, for now, just look at the graph of this x squared minus 1, and as you can see here, the graph is decreasing from the left up to 0, and from the 0 it's increasing. So based on that, the definition from left, which means there is no bound here, so starting from negative infinity up to 0, the graph would be concave downward because the first derivative is decreasing. And from 0 to the positive infinity, the graph would be concave upward because the derivative is increasing. You see that? So similarly, the graph of function is concave. Yeah, so that's the same conclusion here. And the most important thing we're going to discuss next in the theorem, the next theorem shows how to use the second derivative test of a function f to determine interval on which the graph of a function is concave upward or concave downward. That's the test. Theorem 4.7, test for concavity. So let's say you have a differentiable function f, meaning you will be able to find out the derivative of that function. But for this theorem, if you would like to apply this theorem, that function should have second derivative as well. Let's say you found the second derivative, and this theorem says if the second derivative is positive on any interval, then graph on that interval would be concave upward. So find out the second derivative, and if it's positive on interval I, then graph would be concave upward. If the second derivative is negative on the very same interval or any other interval, then the graph would be concave downward. So it's just finding the first derivative and second derivative and finding either second derivative is positive or negative on the interval. Let's say one example, determine the open intervals on which the graph of f of x equal e to the power negative x squared over 2 is concave upward or concave downward. We use this theorem. We need to find out the second derivative, and this is the exponential function. So we should use derivative of exponential function. Let's say you have e to the power g of x, then derivative of this function is g prime of x times the same function e to the power g of x. That's the chain rule. In this case, g of x is negative x squared over 2. So the derivative of negative x squared over 2 is, by using power rule, it would be negative 2 times x over 2, which is negative x. So using that fact, I can find the first derivative. We can find the first derivative, which is negative x times e to the power negative x squared over 2, but we need to find the second derivative as well. So as you can see here, this is the product of two different functions. So for finding the second derivative, we can apply the product rule. And by using the product rule, this is what we are going to get. And because we are planning to use the theorem where we need to find out the second derivative is either positive or negative, for that, we have to equate this second derivative to 0, and that will give us a boundary. So when I try to solve this equation, because this is exponential part, this is not equal to 0, the only part would be 0, could be 0 is x squared minus 1. So x squared minus 1 equals 0. If you solve this quadratic equation, that will give you two different options, x equal plus 1 or minus 1. So at plus 1 or minus 1, second derivative is 0. So now that gives us boundary points, so negative 1 and positive 1. So second derivative of this function is 0 at negative 1 and positive 1. And now on this interval, or this interval, or this interval, we need to find out either second derivative is positive or negative. So as you can see here, this is the left interval, this is the middle one, and this is the right interval. For finding the second derivative on this interval, we need to pick a testing point from each of them. So let's say from the first interval, we're going to pick x equal negative 2. From the second interval, we're going to pick x equal to 0. And from the third interval, we're going to pick x equal to 2. This testing value could be anything from that interval, okay? It's not, exact value you need to pick. You can pick anything from here, but be smart and pick, which gives you simple calculation. When you put x equal to negative 2 in the second derivative, whatever we got here, this one, when you put x equal to negative 2, so second derivative would be positive. When x is 0, if you plug that value back here, so remember second derivative is e to the power negative x squared over 2, x squared minus 1. So if you put x equal to 0 here, that would be negative. If you put x equal to 2 here, that would be positive. So by looking this table, we can say that second derivative is positive here, negative here, and positive here. That means from the theorem we were just discussing 4.7, if second derivative is positive, the curve is concave upward on that interval. If the second derivative is negative, the curve is concave downward on that interval. And that's what we found here. So the curve is concave upward, downward, upward. If you try to use some graphing utility like a graphing calculator, or just plot this function using some graphing tool, this is the graph you're going to find, and you can check that your graph is concave upward, downward, and upward on this three interval like this. Okay. So the next topic is points of inflection. That means let f be a function that is continuous on an open interval and c be a point in the interval. If the graph of f has a tangent line at the point c comma f of c, so let's say there is a graph and there is a point c, and then if at that point you can draw a tangent line, then this point is point of inflection of the graph of f when the concavity of the f changes from upward to downward or downward to upward. So this point is called point of inflection if the concavity of the graph is changing at that point. So that's called point of inflection. So theorem 4.1, point of inflection. If a point is a point of inflection of the graph of f, then either the second derivative at that point would be 0 or second derivative does not exist. So that's the theorem 4.8. Let's do this one example, determine the points of inflection. So remember, point of inflection means a point where concavity changes, and if that is a point of inflection, the second derivative at that point should be either 0 or does not exist. So we're going to find out the first derivative and then second derivative. So the first derivative is 4x cubed minus 12x squared using the power rule. Second derivative is again 12x squared minus 24x using the power rule. And now we're going to find out the points where the second derivative is 0. So by doing that, we're going to find 2 points, x equal to 0 and x equal to 2. And now we're going to find out either these points are points of inflection or not by finding the nature of the second derivative, to the left and to the right of these points. So like we did in previous example. So here is the interval. There is a 0, there is a 2. So there are 3 intervals. We're going to check we're going to check the second derivative, and as you can see here in this table, and these are the testing value, x equal to -1 from this interval, x equal to 1 from this interval, and x equal to 3 from this interval. By plugging this testing value back in the second derivative, which is if you go back to the second derivative here, you can see this is where you can put the value for this testing value, and then that's going to help us for finding the second derivative at those points. And here the second derivative is positive. On this interval, second derivative is negative, and on this interval, second derivative is positive one more time. So on this interval, the function is concave upward. It's downward. So look at here, it's changing the nature from concave upward to concave downward at point 0. So from to the left of the point 0, the concavity is concave upward. To the right of the point 0, the concavity is concave downward. So this point 0 is an inflection point. Similarly, when you go from left of 2 to the right of 2, look at here. On this interval, the curve is concave downward, but on this interval, the concave is concave upward. So it's changing the nature at 2. So that's the reason 0 and 2 are the 2 inflection points. Okay. At 0, the value of the function is 0. At 2, the value of the function is -16. So these are the 2 inflection points. So if you use some kind of graphing utilities or plot the graph of this function, this is what you are going to see. And as you can see here, at 0, before 0, to the left side, the graph was concave up. And after 0, the graph is concave down. At point 2, as you can see here, to the left of the 2, the graph is concave down. And to the right of the 2, the graph is concave up. So this is another example. The converse of the theorem 4.8 is not generally true. That means second derivative 0 does not always gives you inflection points. So this is the one counter example. For this function, if you try to find out the second derivative at 0 is 0, but this is always concave up. So this is not the inflection point. So this is just the reminder that if this is your inflection point, then either second derivative would be 0 or second derivative does not exist. But second derivative 0 does not mean that point would be always inflection point. Like in this example, here the second derivative is 0, but this is not an inflection point. To find out whether it's inflection point or not, you need to, the graph should change the nature from concave up to concave down or concave down to concave up. But that's not the case in this example. Second derivative test. The second derivative test. This is very, very important test. It says if the graph of the function f is concave upward on an open interval containing a point C, and then first derivative at that point is 0, then the value of the function at that point must be relative minimum of f. So look at here, concave upward, that the first derivative at C is 0. That means the tangent line is horizontal tangent line like this. Then it has to be the value of the function at this point is relative minimum. And the opposite to that, if the second derivative, the graph is concave downward, which is second derivative is negative, and then the first derivative is 0, then at that point you are going to get the maximum value. So that's the second derivative test. So let's summarize that second derivative test in theorem 4.9. Let f be a function such that the first derivative of the function at C is 0. And let's assume that second derivative of the function does exist. And the second derivative at C is positive. That means the function has a relative minimum value. And if the second derivative is negative, the function has a relative maximum value. So you can find out the local maximum or local minimum value by using this second derivative test. Okay, but if the second derivative itself is 0, then this theorem, this test fails. So you are not be able to say either, that's a relative maximum or relative minimum. Let's look at one example. Let's say this is the function. We would like to find out the relative maxima, or extrema means relative maxima or minima whenever it's possible. So by using the second derivative test, we need to find out the first derivative first, which is by using the power rule. That would be negative 15x to the power 4 plus 15x to the power 2. We also have to find the second derivative, because we need to check the second derivative by using the power rule one more time. So this is our first derivative. And then because we need to check where this first derivative is 0, so if you equate this expression with 0, then either x equal to 0 or this expression gives you negative 1 and positive 1. So these are the 3 points where the first derivative would be 0. So these 3 points are called critical numbers of the function, where the first derivative is 0. That's called critical number. Okay, so what's the second derivative? Second derivative, if you check, this is the second derivative by using the power rule. And then if you use the concavity test one more time, you can see that second derivative at negative 1 is positive, at 0 is 0, at 1 is negative. So that means we have this second derivative positive. So that means at this point, we will have a relative minimum value according to the previous theorem, theorem 4.9. If the second derivative is positive, we get the relative minimum value here. If the second derivative is negative, we get the relative maximum value here. In this case, at 0, the second derivative is 0. So that means there is nothing. Test fails. If you use some graphing tools and plot the graph of this function, this is what the graph of the function look like. As you can see here, at negative 1, there is a relative minimum value. And at positive 1, there is a relative maximum value. Relative means it's a local. It's not the largest or smallest value. So we can find the relative maximum or minimum by using the second derivative test.